All right, here's a video on 8.5, reaction energies. There was really two topics in this lesson. For one, we learned how to write a thermochemical equation, and then number two, we learned how to draw a reaction energy diagram. Let's start off with writing a thermochemical equation. Sounds big and fancy, but it's actually not that bad. Let's break down this word thermochemical. Therm is referring to like thermometer, and so that means heat. And then chemical, well, chemical equation, right? We actually already know how to do that. And so, you know, what this is saying is a heat chemical equation, a chemical equation that also has heat in it. And so, you know, let's go through that idea of like, we know how to write a chemical equation. What we're gonna add is just heat. So start off with write a chemical equation for the burning of methane, right? We know how to do that, right? Remember in 6.6, we learned about combustion reactions, regular chemistry, you didn't learn that, but AS, right? We did learn that, right? We learned that anytime you have burning, basically, it's gonna be something, whether it be some sort of CHO molecule or magnesium, or it's gonna be something with O2, and then what we're gonna form is CO2 plus H2O. Right, that's the equation for burning, for combustion. And so here, you know, we can also balance it, right? We have 4 hydrogens, 2, so we're gonna put that. Now we got 2 plus 2, 4 oxygens, so we're gonna put 4 oxygen here. Okay, and so that looks like it's balanced, I think. And so, let me just check that real quick. Yep. I think, 4, 2, 4 hydrogen. Yeah, that's balanced. Cool. Now, so so this is a chemical equation. It's a great chemical equation. But you know, the thing is, when you know you have the burning of methane, right? What we're doing is we have fire, right? And fire feels hot. Fire, it's releasing energy. And so technically, it's true that actually here, another kind of product, right? Something that we produce here is energy, right? Energy is also produced as one of the things of this chemical equation. We haven't really considered that though yet. When we've been talking about chemical equations, we've just been talking about, oh, you know, what are the material, the matter that's being created. But now we're also going to start talking about energy, right? Because that's what this unit's about. So yeah, one of the things that's produced is energy. Now specifically, it turns out that the heat of this reaction, basically what gets produced when we use up the molar, the stoichiometric molar equivalencies here, when we use 1 mole of CH4 and 2 moles of O2, it's specifically 2,220 kilojoules. And so we can write it out like this. The delta H, the enthalpy, or the heat of reaction, is equal to 2220 actually kilojoules per mole. What that means, this is what we call the heat of reaction, and it is the amount of energy used or produced when the number of moles used in a reaction is equal to the coefficient of the reactants. Meaning here, right? What's the coefficient of our reactants? Our reactants are CH4 and O2, right? So basically, when we have 1 and 2, when we have 1 mole of CH4 and 2 moles of O2, when we use up those amount of reactants, we will produce 2,220 kilojoules, right? Let me just write that down for you guys. Cool. So that's the heat of reaction. That's what it is here. And so there's actually 2 ways that we could write this specifically, right? So this is kind of our general form. But if, we want to be more specific, there's two ways that you could write this. You could write it like this, where you say, okay, well, CH4 plus 2O2 yields CO2 plus 2H2O, and the heat of the reaction is positive 2220 kilojoules per mole. You could write it like that with kind of the delta H at the end, or another way of writing it is you could say, well, CH4 plus 2O2 yields CO2 plus 2H2O, and another one of the products is 2,220 kilojoules of energy. And so that's another way of writing it. You want to be comfortable with both, kind of having it as a delta H at the end, or here, right, technically this is kind of like as a product of sorts, right? Now do note that we're putting it here as a product because this is an exothermic reaction, right? In an exothermic reaction, heat is being released, heat is kind of it's going out, right? And so it's one of our products, it's one of the things we produce at the end. However, if this was an endothermic reaction, it would be different, right? So let me give you a quick example of an endothermic reaction, right? For an endothermic reaction, so a classic example of an endothermic reaction is this one. Ammonium nitrate breaks up into NH4 plus NO3 minus. This is the reaction in a cold pack. And so this is endothermic. Basically, what happens endothermic, right, is energy gets it gets sucked in. And so here, the heat of reaction is going to be positive 25.7 kilojoules. And so yeah, we see that heat is being sucked in. And so we could write that here, for NO3 yields NH4 plus NO3 minus. So delta H of reaction is equal to positive 25.7 kilojoules per mole. That's actually, sorry, that should be kilojoules per mole. So that's one way of writing it, but the other way of writing it is kind of like, if you're sucking in energy, right, for the reaction to happen, that's kind of like it's a reactant, right? It's needed for this reaction to happen. It's a reactant, basically, right? We suck in that energy here. And so we put it here on the left side as a reactant. And so that's another way of doing this. And so, yeah, you can do it like that. Now, do note, and I'm sorry, I apologize, I messed up here. Do you see what I messed up on? Right, for an exothermic reaction, which was here, right, this should be negative. So, my apologies. If you saw that earlier on and you were confused, I apologize. That should have been negative, right? Because exothermic, we were giving out negative 2,200 kilojoules. And so here also, there, it should have been negative 2,220 kilojoules. Yeah, do note though, here you want to put negative, right? It's still positive, meaning because it's like a product, right? And so it's, it's giving out at the end. So yeah. Cool. Okay, so that's how to write a thermochemical equation. You could do it like this, you could do it like this. Please know how to do both though, just so you can, in case on a test it comes up in either way, or it asks you for it in either way. So that's how to write a thermochemical equation. The second thing we learned how to do was drawing reaction energy diagrams. And reaction energy diagrams are actually relatively simple. They're basically graphs where we have time basically on the x-axis, also known as reaction progress, and energy on the y-axis. And they look different for exothermic versus endothermic reactions. Remember that in an exothermic reaction, right? Exothermic, and so heat energy is exiting. Energy exiting, right? So therefore, we must be losing energy over time. And so what it's going to look like is, if you have here at the beginning of our reaction where we have our reactants, what's going to happen is as the reaction progresses, at the end of it, we're going to be down here. So for our products, we're going to be down here. Now, the course this takes, students might think that it should just go straight down, but it actually doesn't. It turns out that actually you need to go up first. This is what we call our activation energy. We need some amount of energy that we put in at the beginning, in order for the reaction to kind of happen, to kind of get us started. And so we call that EA, energy of activation. The way you can kind of think about it is kind of like, if you're going to push a cart, right, at the shopping mall or shopping center, or what do you call it? Grocery store, sorry. At the grocery store, if you're going to push a shopping cart, especially if that shopping cart is heavy, you got to put in a lot of energy at the beginning, right? But then once it kind of gets going, right, it gets going and it can move and it's not as hard. You don't have to put in as much energy, right? But you got to put in that initial investment of energy at the beginning. Or kind of like, if you're studying, you got to really make a lot of effort at the beginning to kind of get yourself comfortable, right, and get yourself motivated and doing it. But once you're doing it, it's actually not that bad, right? And so here, it's the same thing here. We put in some energy at the beginning and then the reaction kind of go and progress, and that's then it looks like that. And so this is what an exothermic reaction energy diagram looks like. Now the other thing that we can label here is the difference in energy from here to here. Okay, so the difference in energy from the reactants to the products is going to be this. And that difference in energy is the energy that's given off, right? That's the delta H. And so we can label that as well. So there's two things that you can get out of a reaction energy diagram and two things that you need to know how to label. For an endothermic reaction, it's the opposite, right? Your reactants, we start off at lower energy for the reactants, and then remember enter. So heat/energy is entering here, right? And so what we're going to have is we're going to have a higher energy at the end. And so similar here, right? Again, we're not just going to look like that. That's not what's going to happen. Rather, we're going to have some amount of energy we're going to have to put in at the beginning. We're going to have to go up even higher than we would have to otherwise, and then eventually we can go back down. And so this entire thing, we call that energy of activation. Okay, this entire thing is EA, and then still the difference between. I'm sorry, I should have made this the same. I should have flipped the colors, so apologies about that. But this is going to be the delta H. Okay. So that's how you draw reaction energy diagrams, and that's the two things that you can label in it. Do some practice. Hope that helps. Let me know if you have any questions.